There we go. Over to you guys.
Okay, thank you very much, Amin, for this kind introduction. So just before I start, I just want to mention that this work was conducting while Paul was visiting the flowers team in Bordeaux. So I'm going to present our recent work, which is called Learning to Guide and to be Guided in the Architect Builder Problem. To start with, I'm going to start with humans. So humans are really incredibly good at teaching and learning from others. And what's kind of impressive is that they can do so in contexts where there is no shared language and very little common ground. So here you have a small video of a child who's learning to stack objects, and because it's congratulated by a social partner, his parent, he manages to correctly stack these objects. So this kind of interactions and involve communication, and there is a field that studies how humans can develop new forms of communication, and this field is called experimental semiotics. And inside experimental semiotics, there is a particularly interesting experiment that I want to talk a bit about because it's a source of inspiration for our project. So this experiment is the co-construction experiment by Vollmer et al., which really aims at studying the underlying mechanisms required for the emergence of communications. And this study is conducted with two agents, an architect and a builder, which are located in separated rooms. So in this experiment, the architect has a picture of a construction target, and the goal of the builder is to reconstruct the construction. However, the builder has no clue of the shape of this construction. So the architect cannot act on the blocks because he is in another room, but it can send abstract and neutral messages thanks to a button box. And the architect is also seeing the workspace of the builder thanks to a video stream. So in this task, the two agents need to agree on a communication protocol so that the builder can correctly construct the construction. So there are key aspects in this experiment. So first, it's important to notice that there are asymmetric roles. So only the builder can act on the blocks, and only the architect knows what to do with those blocks. Another key aspect of the experiment is the fact that the communication is restricted. It's not face-to-face. The communication is restricted because this experiment aims at studying the birth, the emergence of communication. So we don't want the agents to be interacting face-to-face because otherwise they will be using cognitive biases, such as smiling when something good is performed by the builder, for instance, or giving a thumb up. And really, we want to get rid of that because we want to study the emergence of communication. So instead, the architect is using neutral symbols that have no meanings, no a priori meanings, but also that are chosen so as to be not related to the task at hand. So here is just a small diagram summarizing the interactions between the agents. So the architect sees what the builder is doing thanks to a video stream, and the builder can see the messages from the architect on a screen. So this experiment is kind of cool, and also it's a challenging task. Oftentimes, when we ask the participant to perform this task, they judge this game as impossible or really hard to perform. And it's challenging because the builder needs to simultaneously learn the task while also learning the meaning of the messages. And on his side, the architect needs to adapt to the reaction of the builder. So there are really various dynamics in this experiment. But luckily, the Coco game is solved by humans. But it's important to note that it takes a lot of time for the pairs to converge on a protocol. I think that the pairs were playing this game for about 20 minutes before solving it. And it's also important to note that the solution that they reach is not fancy. The pairs often converge to a kind of positive negative feedback, which basically involve the architect saying a good message when the action performed by the builder is bringing the solution towards the construction, and negative feedbacks when it's not the case. So in our project with Paul, we wanted to study what happens if the two agents that I just described are artificial agents. So for that, we came up with a numerical simulation of the co-construction experiment. And we introduced a new asymmetrical interactive learning setting. So we have the same kind of agents, an architect and a builder. And the builder is taking action in a small environment that we call build world, which is basically a 2D grid world where there are blocks that can be manipulated in order to construct shapes. So in our framework, the architect knows about the goal to perform, so the shape to reach, but it cannot take actions in the environment. It can only send messages to the builder. We also assume that the architect has access to the transition function of the environment, and because it knows about the goal, it has also access to the reward function. On his side, the builder does not know anything about the goal, so it does not have any access to the reward function, but it can take actions, and it can see the messages produced by the architect. And messages are just one-hot vectors of a predefined size, but they have no a priori meanings. So on the left here, you can see a small diagram of the kind of interactions between the agents, and a more formal one on the right, where you can see that only the architect perceives the reward, and the actions of the architect are messages that are perceived by the builder, and then the builder takes action that will yield the transition in the small build world.
One question from Nishan.
Yeah, so I was wondering if there's one-to-one correspondence between messages and the number of blocks or the color of blocks in the experiment.
So we carried out experiments with different sizes of vocabulary. So it depends, but there is no direct mapping between the size of the number of blocks and the size of the vocabulary. Does it answer? Do I answer your question?
Yeah. So is the vocabulary size larger or smaller than the varieties and colors of the blocks?
So so the size of the vocabulary has a strong impact on the solution, and it's larger than the number of blocks. But it's not for this reason that we can get to that later on when we will discuss the results, because we will.
Sure.
So for our solution, the size of the vocabulary is 18. Let me go back to the presentation. Yeah. So now that you know a bit the setup in which we are located, let me present some reason why this architect builder problem is an interesting problem inside AI. So first, it's a good problem for fundamental research because it allows us to gain fundamental knowledge on how we can model the emergence of communication in such an asymmetrical context. But also, it shares similar assumption with real-world applications. In particular, it has same assumption as brain-computer interfaces. So here you have a small picture of a BCI. Basically, it's a robotic arm which is controlled by brain signals. And for such system, it's really hard to define a reward function for the robotic arm. And we can draw a parallel with the architect builder problem, where the brain signals will be the architect messages and the robotic arm the builder that makes the action. And if one big issue with BCIs is that it needs to be calibrated to each human. And we can see the problem of the architect builder problem as where the builder needs to simultaneously learn the task and learn how to perform the task. And we can see that it can be equivalent to doing online calibration of BCIs.
One question. Can
Yes,
you
sure.
clarify what you mean by emergence of communication? My impression was that the communication channel was already established.
Yes. So there is a medium for the agents to communicate, but then the builder needs to associate a meaning with each messages. So when we say that communication emerges, is that initially the messages have no meanings. They are not related to any kind of actions or goals. But as you interact, as the two agents interact, then the agents can associate meanings to these messages. So it's really a high-level definition, if you could say, but it's by meaning you can interpret various things, and you will see that in our case, meanings are associated a lot to actions, but it can be anything else.
Yeah, thanks. And one question about the previous slide. In the diagram,
Yes.
I guess the architect and the builder they see the same state. Is that the
Yes,
case?
exactly, yes. And as you can see, there is also a sequentiality that is imposed by the definition of the problem. So first, so the builder needs to wait for a message from the architect to act.
See. Thanks. Yeah.
So moving on to a third reason why it's an interesting problem, it's also because it's new in the field of multi-agent learning. So if you look at most of multi-agent learning systems, they are often giving access. So all the agents have access to the reward function, and all agents can act. And in our new setting, I just want to remind you that the builder never sees the reward, and the architect never acts in the environment. So I hope that with these few slides, you have a good setup for the rest of the presentation, because now Paul is going to talk about the solution that we propose to this problem and the results that we got.
Yeah, can you all hear me and see my screen?
We can hear you.
And
We're
now you
waiting
can
for
see
you.
it.
Yeah, we can see the screen now.
Perfect. Thanks. So let's dive a bit deeper into the interaction of the agents, and let's take the point of view of the architect first. So the architect is going to observe a state, and then its policy is to choose a message. And this message is going to be used by the builder alongside the state to produce an action, and that this action is going to have the state transition to a new state, so the environment transition to a new state, and is going to generate a reward. And like Tristan said, the reward model as well as the transition model are known to the architect. So we see that provided that the architect can learn a model of the builder's behavior, he can then be thought of as being evolving in like a MDP that is more classical to, it's more similar to what we are used to, right? And the new reward and transition models are expectations with respect to the builder's behavior. The thing is that now if the builder's behavior changes, then so do the transition and the reward model. So we have non-stationarity. And to palliate to that non-stationarity, we are going to rely on a high level prior to communication that is called interaction frames or pragmatic frames. And that states that agents that interact and learn sequentially are more successful at emergent communication. And in our case, we are going to implement that by having the agent learn sequentially, and this will restore the stationarity of the problem. And I'm going to show you in a few minutes how we do that in practice. Now, if we take the point of view of the builder, it may seem a bit more complicated, but actually it's pretty much the same idea. And we can blend together states and messages and call them, for example, observations. And then we are back to a more classical MDP. But the real challenge is not here. The real challenge is that the builder has not access to the reward function. It has not access to the reward of the environment. So it has no learning signal. So the real question is that, okay, but how is the builder going to learn anything? And to deal with that, we're going to rely on another high-level communication prior that is called shared intent, that has been shown to be necessary for the emergence of communication, both in practice and in theory. And it states that the agents are optimizing toward the same goal. So this means that the builder, even if he doesn't know this objective, he can assume that it has the same objective as the one the architect is optimizing for. And in this case, is for example, like building this target structure. Both agents aim at building this target structure. And so now that we have these two points of view, it's interesting to see that because these agents are interacting together, they are experiencing the same state, messages, action trajectories, right? And this is really interesting because if we add the shared intent prior, then we can say that a trajectory that has been generated by the architect, when it was maximizing its reward that is aware of, it can be seen by the builder as a demonstration on how to maximize this objective. And because they share this objective, it can be seen as a demonstration of how it should behave. So actually the builder can use trajectories that it generated itself when it was guided by the architect as demonstration to improve its policy. And so because the builder is going to imitate itself, like previous trajectories of itself, we call this self-imitation. And so this is going to be the learning mechanism that the builder is going to rely upon. So our full solution is called architect builder iterated guiding, and it relies on two interaction frames. So we have the modeling frame and the guiding frame. In the modeling frame, the architect is going to collect data about the builder's behavior by sending random messages and observing how the builder reacts. Once it has collected enough data, it's going to use behavioral cloning to learn a model of the builder's behavior. Once this model is learned, we can transition to the guiding frame, so the next frame. And in this guiding frame, the architect is going to use this model of the builder alongside his reward model as well as the environment model to do planning and pick messages that will maximize the reward. So it's going to select messages that will yield action from the builder that will optimize the reward. And so during this guiding phase, the builder is actually collecting this guidance data. And once it has collected enough guiding data, it can use this guiding data to do self-imitation on it and improve its policy. And once this is done, we go back to a modeling frame and we iterate over learning between modeling frames and guiding frames. So the task that we consider, so here we have a vision of an illustration of our environment. So we have this builder that has access to this gripper and can move blocks around. And so we started with really simple tasks. So tasks such as grasp. So you succeed if you grasp any block. Another task that is called place, where you have to place any block, but at a specific location that is known only by the architect. And then you have two additional tasks that are like building an horizontal line or building a vertical line. And so here we have the results. So here we trained so the DIA, so the pair of agents, on each different tasks. you can see here. And we have an additional task that is like when you train on all of the tasks at once. So meaning that at the beginning of an episode, we randomly sample the task for this episode. And here we see the different bars are the testing goals. So we wanted to see if, for example, a communication protocol that the agent learned when learning to solve the task grasp, if it could be reused to solve the other task. And what we see is that expect for the grasp task, that is really simple, this seems to work pretty well for the other task, especially for place. Meaning that if you learned a communication protocol on place, then you can reuse without retraining this communication protocol to succeed at all the other tasks, and your success rate is pretty much the same as if you were trained directly on this task or if you were trained on all of the tasks at once. So this was really encouraging, and we wanted to try more complicated structures. So these are the structure you can perform if you were trained only on the place task. And here you have some rollouts. So at this point, we wanted to understand a bit like what were the learning mechanisms that were happening during learning. And so we started with simple ablations. So the first ablation was to have like a lower bound on performance. And so it's just like, how does a builder that selects random action performs? And that's like the green bar. So it gives us a lower bound. And then we wanted to see how does what if the builder is not learning? What if the builder has a static policy that is always the same and that the architect knows of and can use with planning to a bit like control it? And so we tried a stochastic policy. So it's a randomly initialized Boltzmann policy. And the builder samples action from it. And a deterministic one that is like the argmax of this randomly initialized Boltzmann policy. And we see that if with these static policies, well, the pair performs quite poorly. We then wanted also to see what was the impact of this like shared intent prior. So for that, we tried this ablation, like no intent ablation, where the builder does self-imitation, but it doesn't do self-imitation on guidance data. It only does self-imitation when the architect is sending messages at random, meaning that it's not optimizing for its own objectives. And we see that except on the simple tasks, such as grasp, this fails on other tasks. So to analyze more this phenomenon of like this shared intent phenomenon more in depth, we tried a toy problem. So it's like a two-armed bandit. And we were looking at the evolution of the builder's policy. So here we have like the initial builder's policy, where it's just like probabilities of taking an action depending on the message you get. And we can see here the evolution of this policy throughout iterations of training. And we see that we have two really interesting mechanisms. The first one is illustrated here, and it's a forgetting mechanism. So associations, so let me start that way. So when if the architect is not guiding the builder with a message, because for example, this message will yield a high probability of losing, the builder, because he's not doing self-imitation on that specific message, is going to forget the association between this message and actions. And we have another mechanism that once a favorable association is made between message and action, then it's going to be reinforced throughout the learning. So we have these two really interesting mechanisms that one enables the pair to forget associations between messages and bad actions, and another one that enables the pair to reinforce associations between message and good actions. And so this happens when we have the shared intent, but if we don't have shared intent, what happens is that we only have the reinforcement mechanisms that is just going to reinforce the initial conditions, because in that case, you don't have good or bad actions because you don't have a guidance. And so we wanted also to see like the evolutions of the metrics throughout learning. So here we have like the success rate throughout learning, and we see that if we don't have the shared intent prior, then the performance does not improve over time. But interestingly, if we look at the entropy of the builder's policy, so it's like the stochasticity of this builder's policy, we see that it decreases for both methods, meaning that the builder's policy become more and more deterministic. And this is related because actually both methods have these reinforcement mechanisms that is going to make the policy more and more deterministic. And finally, maybe the more interesting finding is when we look at mutual information between actions and states, or between actions and messages for the builder's policy. And what we see is that when you have the shared intent prior, so the solution that works best, you see that the mutual information between messages and action increases, whereas the mutual information between states and actions eventually decreases. And there is this important crossing point that indicates the point at which the builder is selecting his actions more based on the messages that it receives than the states. And this is something that you really want for like an efficient communication protocol, and in order to be able to guide a builder toward a specific goal. So yeah, that's pretty much it for the presentation, and we're happy to take a question now.
Thank you, Paul and Tristan. Are there any questions? Yeah, we have a question from Nishan.
Paul, can you please explain like how the model learning phase helps in the other phase? Like you said, like in the beginning, you are going to sample uniform actions or like uniform messages, and then the builder will actually learn associations, right? Like how does this learning help in the later phase?
Do you mean the learning that is done by the architect or by the builder? Because both are learning a model.
Yeah, both of them from their perspectives.
Yeah, sure. So if you go back to the method, like, so for the architect is, I think it's quite, it's more simple to understand. So the architect is going to collect data on the builder's, about the builder's policy. And so it can derive a model of this builder policy. And once you have this model, then you can use this model to plan how your messages are going to influence the actions that are going to be taken. And so eventually how these actions are going to influence the reward. And so you can do planning and optimize your reward with that. And then the other learning part that is done by the builder is when you have trajectories that are collected when the architect is maximizing its reward. These actually are demonstration of how to maximize the architect's reward. But because the builder and the architect share the same objective, the builder can use this as a demonstration on how to maximize this objective. And this is how you can improve the policy of the builder, right? Does this make sense?
Yeah, totally. So I had a follow-up question, which is builder's behavior would be non-stationary, right? Because he doesn't have, or like builder doesn't have any information about message association. So like behavior is evolving, and architect would have to account for that when it's planning, right?
Exactly. That's why once you did a guiding phase, a guiding frame, then you go back to a modeling frame, because the builder's policy had changed. So the architect has to adapt his model. So this is why you were always like switching between these interaction frames.
Okay. And this switching keeps on continuing forever?
Yeah. At one point when you feel that the solution has been built, you can stop, right? But you have to end by a modeling frame, obviously. Okay. Because otherwise, but what we see also in the learning curve is that eventually the builder's policy stop changing across iterations, right? So eventually it converges.
Okay. And when it converges, like, can you draw associations between the messages to actions?
Do you mean like visually or?
Yeah, visually. Like if architect sends one hot encoding of some vector, what does builder actually do with that one hot encoding? Like what action does builder take of that sort?
Yeah,
Yeah,
so
I think
yeah, go ahead, Tristan.
we cannot. I mean, we can do it, but the thing is, we in the method we don't have any prior to impose the fact that messages should have similar meanings across states, meaning that each time you see a new state, the one hot position of a certain meaning can change from one state to another, which means that it's really hard to interpret the results. But so that's why we also provide the mutual information between action and messages. But we don't have a real mapping between, okay, if I am in the third position of my one hot vector, this means that I should do that, because the position will always change depending on the state you in. Does it make sense for you? Or
Yeah.
yeah.
Thanks.
Are there any questions? There is one question in the chat. I think from Vincent. I think I understood that the frames were learning phases. Do the builder and architect know in which frame they are and when to switch? Doesn't this imply that there is a communication between them?
So yeah, this we chose to enforce like at a high level as like a starting point. But I think what would be interesting is to the first step is to remove like this assumption of like switching between interaction frames and having something more relying on like finite size replay buffer and see how this works, right? Because between having like strict phases, but it was like to deal with the non-stationarity in a first step, like a first solution.
I see. Does it answer the question, Vincent? Yeah, and I have a question. You said how many symbols were in the set that you're using?
Yeah, so we did. Go ahead, Tristan, if you want to take this one.
Yeah, I started a bit explaining this at the beginning of the presentation. So we had 18 symbols, and we saw that there is so increasing the number of symbols allows to solve the task. And we, for instance, if we have a small number of symbols, we cannot deal with this task. For instance, if we only have 2 symbols, there is a collapse. So yeah, so we did a kind of an ablation with which is not presented in this talk, but where we can see the impact of the size of the vocabulary.
I see.
And for that, so there is kind of an explanation to that, is the fact that as Paul explained, we have this forgetting and this reinforcement mechanisms, and we can see that the more messages you will have, the easier it would be to have a favorable association between messages and actions, which will be later on reinforced. So yeah, that and I think this is also important. It's something that is known in the emergence of communication community. In referential games, for instance, I think that there is theories that says that the more messages you have, the easiest it will be for your system to agree on references inside the message.
Yeah, so I guess that makes sense but from one perspective, it's also easier because I mean the number of unique messages that you can create with higher number of symbols is like orders of magnitude more than if you have like just a few symbols, and it requires a more intelligent agent to like use these symbols together and reuse them in a way to convey different meanings. And I guess that's what really intelligent agents would do, using the same symbols for different intents or purposes. And like you said, I guess if you decrease the number of symbols, you cannot solve the task. So I guess it would be interesting to see like a curve or a plot for when this transition happens from, for example, 2 symbols to 16 or 18 symbols, where in the plot we can see the performance increasing.
Yes, that's actually in the paper. I mean,
Yeah.
not a curve, but we have several points.
Yeah. Yeah, we have a question from the show.
Paul and Tristan, this is from RL perspective. So I was wondering, like, uh, is it possible to solve this task without trying to build model and then planning? Like, if it were to be pure online learning, where architect is also learning online and builder is also learning online, like what challenges do they face while learning, and then is it possible to tackle them purely in an online fashion?
Yeah, so this is a good question. So for example, first of all, for the builder, you could not do a reinforcement learning because you don't have a reward. But for the architect, you could. And so we did not try it because I think it would make the problem more difficult, right? Instead of like an architect having to figure out, he knows what he wants to do, he knows how to do it, but he'd have to figure out how to communicate this to the builder. It would have to figure out how to solve like the solution in the first place, meaning that he would have to understand how to stack blocks and how to go from stacking blocks to the target structure. And because we took inspiration from the experimental semiotic experiment, in this experimental semiotic experiment, the architect would definitely know how to do it, right? If the architect would be in the place of the builder and he could like move around blocks, he would be able like to build the target structure without having to learn anything. And so we wanted to be in the same kind of space where you just have to learn how the other agent behaves. But once you know this, you know how to guide it toward the specific structure because you know how to build a specific structure. So this is a much more challenging problem that you're proposing. That it's really interesting, but it's like how you can learn a task and at the same time teaching it to someone that you don't share a language with. So that's a lot of unknown, right? And most of the time, when you want to teach something, you can assume that you know how to do it, right? So,
Yeah, thanks a lot for your answer. It makes sense.
cool. I think there is also another answer in another question in
Yeah,
the chat.
there is a question in the chat. Yeah.
So the question is like, what is the benefit for having to evolve the communication protocol rather than agreeing on a protocol first? This is a separate problem that may create more complexity to the experiment and to judge overall performance. So yeah, that's a good point. It's just that in some cases you cannot agree on a communication protocol beforehand. For example, if we go back to the example that Tristan was talking about, like with brain-computer interfaces, right? You don't know, like every person is going to have different brain signals, and so the arm doesn't know how to exactly like react. For example, how to move with respect to a specific signal, and so this has to be figured out on the fly. That's what's called like online calibration, right? And this is going to be a coevolution between the person using the arm and the arm, right? So you're going to send a signal. For example, you want to send a signal that for you means that the arm should go left, but actually the arm is going to understand this by going up. And then you have to adapt yourself and say, okay, so when I do this, it's actually going up, so I can adapt to this. And the arm at the same time can reinforce this kind of association. Does it make sense? Because like the user and the arm doesn't have like a same a shared way to communicate. Okay, when I do this, I want you to do this, right? You just have a trial and error kind of things, and so this means that you have to evolve actually a communication protocol because you don't have a mapping. And this is exactly like the architect builder problem.
Yeah. Are there any other questions? I think there are no questions, but I want to go back to the points of this communication channel and the number of symbols. I guess one reason for that is that the architect is in charge of like giving the reward to the builder, but builder has no explicit way of giving any reward to the architect, right? Is my
Right.
impression correct?
So go ahead, Tristan, if you want.
I mean, so the architect does not need any reward because it's provided by the environment. But you are right. The communication is one-sided, sort of inside our setup. So there is no way for the builder to ask for anything to the architect, which could be something realistic as well. But in our case, the builder is simply waiting for messages to the architect from the architect.
I see. Yeah, what I was trying to say was that, for example, if I, as the builder, expect one message associated with some action in some state and receive something else, if I could punish the architect for that, maybe that could help building, I don't know, better communication channel with lower number of symbols or something like that. But that's just a rough idea. Yeah.
Yeah, that could be, but also you could imagine a situation where neither the architect nor the builder would like to yield to the others' communication priors, like the other ideas of what mean a message, and then you wouldn't be able to understand each other. And for example,
Yeah.
with the experiments with the real humans, the only pairs that failed were when the architect was not able to put itself in the shoes of the other agent and to realize that to adapt the message it was sending to the behavior. For example, the architect was saying like, okay, when I give you like the red dot, it means go left, and he was not changing regardless of what the other agent was doing. So if you get this kind of egocentric process, then you fail.
I see. Yeah, thanks for the answer. One last question in the chat. How do humans fare in this task as compared to other agents?
So yeah, I think I mentioned it quickly in the introduction. So humans are actually quite slow at solving the task. So they are first a bit scared by the task because they think it's really hard to perform. And so there is a so I'm gonna share a link on the chat where you could see the experiments done by the humans. But what's striking is that yeah, it takes quite some time to agree on the communication protocol, and also the type of protocol that emerges is really not fancy. It's not about associating meaning of an object, or so there is no such associations. It's rather positive, negative feedback. So simply saying, okay, the thing that you just did is good. The thing that you just did is bad, and basically with this kind of protocol, they can solve the task. And you see that this kind of protocol cannot really be implemented in our solution for now because it involves having some kind of memory mechanisms to associate the meaning of messages with what you previously did and not what you are currently doing.
Perfect.
Thanks, Paul, for the link here.
Thank you. And do you guys have anything planned for future work? Or
yeah, so for future work, so first would be like simplifying the current setup. For example, I think the most interesting one would be to remove this like sequential interacting frames that you have a bit like to impose on the agents. So this would be, I think, a really nice direction. And so you want to go for another direction, maybe like integrating the solutions or something like that?
Yeah, I mean, so a major drawback of the solution we have now is that I can kind of teach a builder how to do the task, but the builder is constantly waiting for messages, which means that even if you solve the task in the end, the builder cannot solve the task autonomously, which is kind of sad. So we could add a third step to the method and have the builder learn a model of the architect, so that in the end, in each state, the builder could do a simulation of what the architect would say in this situation, and then predict the correct message and be fully autonomous. So that's kind of a bit far-fetched, but I think it could be a cool experiment. And then there are also experiments that can be made. So I think the solution that we proposed is really a first step towards solving the problem, and it's kind of naive in some sense. But then I think it's also a good setup to study, for instance, different kind of constraints on the communication protocol, to see if we could, for instance, achieve compositionality or interesting features about the type of meanings that are associated to the messages. So yeah, it's just a first step for now.
Perfect. Thank you so much. Thanks for the presentation. The talk is officially ended, so I'm going to stop recording.